NanoHub U, online instruction.
Hey everyone, welcome to lecture 212. In the last lectures, we were talking about how to use the S4Sim graphical user interface to perform S-matrix simulations. Now we'll talk about another tool that has a formulation that's related to S-matrix to solve problems, which is called Camphor. And so, as we discussed previously, there are many problems where you have layers which have different thicknesses, and sometimes these are up to 6 orders of magnitude different, like in the case of LEDs or lasers, or even like a photonic crystal structure. So you may actually think that the natural form of the solutions is semi-analytic in terms of eigenmodes, because if you can just write down a handful of eigenmodes that correctly describe each of the layers, then that makes formulating the transmission between them potentially much easier. And so this is a slight modification of the earlier approach, in which we basically assumed all the quote-unquote eigenmodes are basically plane waves. And so now we're kind of generalizing to say eigenmodes will be whatever they are. So again, we're going to break up the structure into layers, but then we'll calculate the eigenmodes in each layer. And we'll go into more details about what kind of eigenmodes are possible. And then in order to match the boundary conditions, since we don't have like a simple plane wave formulation, we'll need a more sophisticated way to match these different modes across the boundaries, which is called Lorentz reciprocity, which we'll talk about soon as well. And then we'll need to propagate layer by layer using the S-matrix method, just like before, and then apply the inputs to calculate the outputs. So basically, the second step of how do we calculate the eigenmodes is a critical difference from before. And so this is actually somewhat similar to what's called beam propagation method, or BPM. And so it all starts with the Helmholtz equation, which is essentially a combination of two of Maxwell's equations into this sort of form here, where we have a transverse Laplacian plus this epsilon mu times omega squared times phi is equal to beta squared times phi. And so this basically tells you the relationship between the transverse periodicity and the wave vector in this direction, and the frequency and dielectric impermeability constants of the materials that we're dealing with. And so this, of course, is very similar to something that we had before in the S-matrix method that we covered previously. And phi can represent either E or H field, and beta, of course, is eigenvalue in the Z direction. And then that allows us to write down the solutions, much like before, as having these phase shifts as you propagate in the Z direction times some initial E and H field values. Okay, so that's fairly simple. But then what kind of eigenmodes can we get when we do this kind of solution? So there are basically 4 types. We can say the first type is essentially a guided mode. And so the guided modes are represented here. And so these have an effective real part of the refractive index, so it's associated with like propagation, but then there are no losses. And so this is like a perfectly well-guided mode. Now you can also have losses potentially, of course, and then these modes usually associated with a positive imaginary part of the dielectric constant or effective dielectric constant. Or you can think of it also as imaginary propagation method term. And then when you plug that into the e to the minus jk beta, right, then that gives you something that looks like exponential decay as you propagate forward with a positive imaginary n. If you have a negative imaginary n, however, that's usually interpreted as a gain, so it would be exponential increase. So that's also a little bit funny. So we don't necessarily have to worry about that at the moment, but it may come up later. And then the third type of mode we can think about is so-called radiation mode, in which we basically have losses but no propagation. And so then that's shown as kind of this vertical line here along the y-axis. And so those kind of modes basically have loss, but they don't actually propagate forward. So they're just like leaking into space. Okay. And then the final set of modes are essentially complex modes. And so you can see that actually it might be hard to distinguish the complex modes from the leaky modes, except that they have like pairs, basically at kind of a set of like 2 or 4 different points, where you've just basically switched the sign of either the real or imaginary part of n. And so just to look at physically how these modes appear, you can see guided modes basically are highly localized to your waveguide mode. Complex modes, however, are not fully localized because there's essentially a tunneling that allows them to leak power from the middle outside. And then the leaky modes and complex modes have basically a very similar kind of form, which makes sense because oftentimes they show up in the same quadrant, roughly the same area. And then finally, you have these radiation modes that have like all kinds of oscillations that basically reflect the fact there's very little confinement. And this is all discussed in more detail in this thesis from University of Ghent, written by Peter Beensman, if you want to look at more details. In the next lecture, we'll talk about how camphor could be used in subsequent steps like Lorentz reciprocity.